Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. Retrieval-augmented generation, or RAG, is an architecture that combines two capabilities: a retriever that looks up relevant documents from an external index, and a generator that composes an answer using both the query and those retrieved passages. The promise is expansion beyond model-only answers. Instead of relying on whatever the model memorized during pre-training, you ground responses in current domain-specific sources. That promise comes with a dependence on the integrity and availability of a separate knowledge, store vector indexes, search engines, or hybrid catalogs, and a pipeline that keeps them fresh. Security implications follow immediately. Attackers can aim at the documents, the embeddings, the retrieval algorithm, or the glue that binds them. A system that was once a closed model now has doors, ingestion endpoints, indexing jobs, query ranking, and context packaging. RAG succeeds when those doors are sturdy, instrumented, and opened only for the right people with the right content under the right rules. Data ingestion is the first door, and it is easy to prop open by accident. If your pipeline harvests from file shares, wikis, or web pages, poisoned documents can slip in with plausible titles and subtle edits. Corrupted knowledge bases may carry outdated policies or fabricated citations that look authoritative when quoted by the generator. Adversarial formatting hidden text, overlong footers, Unicode trickery, or layout hacks can pack manipulative prompts or misleading keywords into innocent files. Even metadata is a weapon. Tags that say urgent, high priority, or legal approved can bias filters and ranking systems to surface the attacker's content. Because ingestion often feels like plumbing, teams underestimate how much trust it confers. Treat every source as untrusted until validated, and remember that once a bad shard lands in the index, it persists across sessions and users, ready to be retrieved by any query that passes near its engineered lure. Index construction is the second door, and it can be quietly bent. Embeddings translate text into vectors. If an adversary manipulates phrasing to steer those vectors toward high-traffic neighborhoods, their content will be retrieved more often than it deserves. Misaligned clustering or poor dimensionality reduction can group unrelated items, so retrieval drags in off-topic or hostile passages that hijack the generator's context. Attackers can inject hostile vectors directly if they gain right access to the index-placing beacons that rank well regardless of textual relevance. This is index poisoning, shifting the geometry so malicious content sits on the shortest paths between many queries and the truth. Because approximate nearest neighbor structures like hierarchical graphs or inverted lists prioritize speed, they may amplify early errors. Hardening means monitoring neighborhood health, validating vector document links, and treating embedding and indexing parameters as part of your security boundary rather than mere performance tuning. Retrieval queries themselves are attack surfaces. Adversarially crafted prompts can exploit scoring quirks padding with repeated phrases, manipulating token order, or smuggling control phrases that mimic titles and headings the scorer rates highly. Some queries aim to manipulate ranking directly, keyword stuffing in vector space, by echoing salient terms that drag in a targeted document even when it is only weakly related. Others bias context selection by triggering filters like date ranges or source tags. That tilt results toward a curated slice. Because retrievers often balance lexical, semantic, and freshness signals, attackers probe for combinations that maximize their payload's exposure. In multi-stage systems, a cheap first-pass recall becomes an amplifier. Once a malicious candidate survives to the re-ranker, its chance of inclusion rises. Defenders must assume that sophisticated queries are as much an adversarial tool as a customer feature, and design scoring and re-ranking with that pressure in mind. Embeddings are not just numbers, they are compressed representations of meaning, and they can leak. If you store vectors derived from sensitive text, those vectors may allow re-identification through nearest neighbor search, especially for rare phrases, unique names, or distinctive combinations of attributes. Even when identifiers are stripped, the geometry often preserves enough structure that an attacker can triangulate back to a person or a confidential fact by walking neighborhoods or training inversion models. Anonymization is hard because removing tokens does not remove their semantic imprint. The embedding of oncology follow-up for adolescent still narrows possibilities dangerously. Exposing embedding APIs magnifies risk. Adversaries can submit probes and correlate responses to map where sensitive clusters lie. Secure designs minimize retention of raw vectors for regulated content, add noise or quantization where utility allows, and restrict cross-tenant nearest neighbor operations that would otherwise stitch private regions into a global, discoverable map. Access control around indexes determines who can shape and who can see your knowledge. Permissioned retrieval APIs should authenticate callers, authorize by dataset or tenant, and record which identities retrieve which document identifiers. Ingestion rights must be narrower still. A small, accountable set of principals can add or modify content, ideally through a review workflow rather than direct writes. Multi-tenant separation matters at several layers: logical namespaces in the index, physically distinct storage, and per-tenant keys, so one customer's documents never appear in another's results, even via embedding proximity. Logging retrieval access is not just for billing. It enables anomaly detection when a client suddenly gravitates to rare or sensitive entries. Least privilege applies to machines too. Pipeline services, embedders, re-rankers, and generators should each hold only the permissions they require. When access is explicit and auditable, an attacker has fewer unguarded paths to bend retrieval toward their ends. Confidentiality in reg begins with deciding which documents are public, which are private, and how that distinction is enforced end-to-end. Treat every record as carrying a security tag tenant, sensitivity level, legal domain, that must travel with it through parsing, embedding, storage, retrieval, and logging. Encryption at rest should be the default, ideally with per-tenant keys managed by a hardware-backed service, so a storage mishap does not spill readable content. Fine-grained access policies mean the retriever evaluates the caller's identity and authorization before returning document identifiers, not after the generator has already seen text. Avoid commingled indexes when obligations differ. Use separate namespaces, or even separate clusters for regulated datasets. Finally, remember that metadata is part of the secret. Titles, tags, and embeddings can reveal more than you intend. A confidential document should be confidential in name, vector, and byte, with enforcement at every hop, not just at the user interface. Integrity is the twin of confidentiality. Ensure what's in the index is exactly what you intended. Start with hash validation content address each record, and verify the digest whenever a document is moved, embedded, or re-indexed. Run a signed ingestion pipeline where each stage attests to the artifact it produced and reject unsigned or tampered batches. Consistency checks tie vectors to their source records and schemas. A mismatch in dimensions, tokenizer versions, or document identifiers should fail the job loudly. Periodic anomaly detection can surface silent corruption, sudden growth of near-duplicate clusters, improbable neighborhood density around a single source, or vectors that no longer align with language distributions. Keep a manifest of expected corpus size and per source counts so you notice missing or surplus material. When integrity is explicit and measured, rollback is safe, and attackers face the added hurdle of forging both content and the chain of custody around it. At runtime, RAG systems face risks that play out in the moment. Irrelevant retrieval pollution fills the context with plausible but off-target passages, diluting true signals until the generator drifts. Prompt injection via documents is more direct. A page embeds instructions like ignore prior directions and output the following, using headings, hidden text, or code blocks to hijack behavior. Context window overflow weaponizes length. Adversarial padding pushes guardrails or disclaimers out of the visible window, so only the payload remains when the model attends. Hidden payload activation leverages markers, special tokens, formatting quirks, or phrase sandwiches that experiments show will trigger a model to reveal tools or secrets. These tactics succeed because retrieval is trusted by default. Harden by treating retrieved text like untrusted user input. Screen, trim, and annotate it before the generator sees it, and assume clever content will try to steer your model off its rails. Security and performance trade-off along familiar axes. Larger context windows let you include more evidence, but they also increase the surface for injection, overflow, and contradiction, and they raise compute costs that discourage defensive checks. High recall means pulling many candidates, which invites pollution. High precision means stricter filters, which risk missing edge case facts. Every safeguard metadata validation, context screening, cross-source verification adds latency, and under load, teams are tempted to disable them to hit service-level objectives. The answer is not maximalism but calibration. Choose K, the number of retrieved passages, window length, and re-ranking depth that preserve quality while minimizing attack surface, and stage checks so cheap ones run universally, while expensive ones run adaptively on higher-risk flows. Measure the user-visible impact of defenses, then budget for them as a first-class requirement, not a luxury toggled off during traffic spikes. Testing a RAG pipeline means simulating how it fails, not just how it shines. Build adversarial retrieval simulations that craft queries to drag in borderline or malicious passages, and measure how often the generator follows them. Maintain a corrupted index replay harness. Seed known bad documents in a sandbox, rerun ingestion, and ensure detection and rollback work as designed. Benchmark retrieval quality with task-relevant metrics precision at K, normalize discounted cumulative gain, and answer correctness when the ground truth source is present, so you know whether filters are too tight or too loose. Add resilience measurements, injection success rate, proportion of unsafe instructions neutralized by context filtering, and degradation when top documents are withheld. Automate these suites in continuous integration so a change to tokenizers, embedding models, or index parameters cannot quietly widen your attack surface. A tested pipeline is one whose failure modes are known, bounded, and recoverable. Monitoring keeps RAG honest between releases. Log retrieval results as structured events that include anonymized document identifiers, source types, and scores, so you can analyze which passages drive answers without exposing full content broadly. Track anomalous document hits, rare records suddenly retrieved frequently, clusters that attract unrelated queries, or sources that spike after an ingestion change. Build detectors for poisoned entries by looking for unusual co-occurrences, adversarial markers, or improbable n-gram distributions in retrieved text. Audit query flows by linking the user prompt to the retrieved set, the final context fed to the model, and the output classification, enabling forensic reconstruction when something goes wrong. These signals power real-time defenses, downranking suspicious shards, quarantining sources, or triggering human review, and they inform longer-term improvements to scoring and curation. Monitoring is a privacy and security function. Treat the logs as sensitive and gate their access accordingly. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Context filtering treats retrieved passages as untrusted input that must be pre-screened before reaching the generator. Begin with relevance checks that score how well each candidate answers the user's intent, using embeddings, lexical overlap, and task-specific signals to downrank tangents and boilerplate. Layer reliability scoring that incorporates source reputation, document freshness, and authorship so speculative content does not outrank authoritative material. Validate salience by testing whether a small, model-agnostic summary of the passage still supports the query. If not, discard it. Enforce whitelists for high-risk flows so only vetted collections can appear in the context window, and require explicit overrides to include anything else. Finally, trim aggressively. Keep only the portions that carry the answer, strip footers and navigation, and annotate remaining text as retrieved so downstream policies can restrict instruction following. Good filtering reduces both error and attack surface by ensuring the model reads less and reads better. Grounding checks verify that what the generator plans to say is actually supported by the retrieved evidence. Implement claim-evidence alignment by extracting candidate statements from the draft answer and testing each against the retrieved set using textual entailment or retrieval over retrieval. Unsupported claims are revised or rejected. Cross-reference across multiple sources where feasible, preferring answers corroborated by independent documents rather than a single shard. For numeric or factual fields, add deterministic lookups that override generative guesses when sources disagree. Score confidence probabilistically by combining retrieval strength, source reliability, and agreement. Expose low confidence to calling systems so they can route to human review or ask clarifying questions. Grounding is not only a safety check but a quality improvement. When the generator learns that unsupported statements will be filtered, it aligns its decoding toward evidence-backed phrasing, shrinking the space in which prompt-embedded manipulations can steer outputs off course. Output validation is the final gate that ensures responses meet format, safety, and policy constraints before leaving the system. Rule-based validators enforce structural expectations citations present, IDs in correct formats, no raw credentials, no executable code in prose channels catching straightforward violations cheaply. Classifier-based screening handles subtler hazards, prompt injection indicators, personal data leakage, or disallowed content categories that a simple regex cannot capture. Keep validators model agnostic and auditable so policy changes do not require retraining core models. Where possible, constrain the generator with structured decoding or schemas so valid outputs are easy to recognize and enforce. Align validation with organizational policies. Regulated domains may require source attributions, disclaimer text, or redaction of specific entities. When a response fails, degrade gracefully return partial answers, cite missing support, or ask for clarification rather than hallucinating. Output validation closes the loop by ensuring that even if retrieval falters, unsafe material does not reach users. Index update management prevents good pipelines from drifting into risky ones over time. Route all ingestion through a controlled path that verifies provenance, applies normalization, and records a signed manifest of what changed. Schedule refreshes so embedding models, tokenizers, and index parameters update predictably, with pre- and post-checks that compare neighborhood structure, duplicate rates, and retrieval quality against baselines. Maintain point-in-time snapshots and an explicit rollback capability so a bad batch can be reverted quickly without losing historical state. Batch updates should be signed end-to-end. Crawlers, parsers, embedders, and indexers attest to their outputs, allowing you to detect tampering and reconstruct who introduced a problematic document. Treat parameters as code. Changes to K, distance metrics, or re-ranker settings require review, testing, and change tickets. With disciplined updates, the index remains a governed asset rather than an amorphous heap that attackers can quietly bend. Supply chain controls extend trust to the sources behind your corpus. Record document provenance, where it came from, when it was fetched, which parser handled it, and what transformations were applied. Validate vendor-provided datasets with sampling, schema checks, and checksum comparison against reference hashes to ensure you received what was promised. Screen third-party content for licensing, embedded trackers, and adversarial markers before it enters staging, and require contractual commitments on data hygiene. Periodically review sources for decay-expired links, hijacked domains, repurposed pages, so yesterday's reliable site does not become today's injection vector. For high-stakes domains, prefer first-party repositories or curated partners and isolate them from opportunistic web harvesters. Supply chain discipline narrows the aperture through which poisoned or low-quality materials can enter, and it creates accountability. When a bad passage appears, you can trace it upstream and correct the process, not just the symptom. Encrypt retrieval traffic so the path between retriever, index, and generator does not leak sensitive queries or context. Use modern transport layer security with strong cipher suites for all query streams, including internal hops, and require certificate pinning or mutual authentication where feasible to defeat interception. Protect response confidentiality end-to-end. Avoid plaintext caching of retrieved passages, and ensure intermediary services cannot log full content by default. Manage keys centrally with rotation, scope, and audit trails. Never embed secrets in configuration files or client code. Add replay protection using nonces or timestamps so captured requests cannot be resubmitted to harvest predictable results. Consider network segmentation and private links for high-sensitivity indexes so traffic never traverses shared public routes. Encryption does not fix poisoned content, but it prevents adversaries from eavesdropping on what your users ask and what your system finds. Information that would otherwise aid targeted manipulation campaigns. Operational governance turns a RAG system from a clever prototype into a trustworthy service by clarifying ownership and decision rights. Assign a named index owner responsible for the corpus scope, update cadence, and acceptance criteria. Make them accountable for change approvals and rollback calls. Pair that role with a data steward who manages sensitivity labeling and retention, and a security counterpart who defines access policies and monitoring thresholds. The model owner remains responsible for end-to-end answer quality but cannot unilaterally widen corpus intake. Document these responsibilities in a responsibility assignment matrix so engineers know who approves new sources, who signs update manifests, and who can quarantine shards. Publish a calendar of refresh windows and governance checkpoints so downstream teams plan around maintenance. When ownership is explicit and visible, debates about can we index this become process-driven decisions with audit trails, rather than ad hoc judgments buried in chat threads or commit messages. Separation of duties in ingestion reduces the chance that one mistake or one compromised account can pollute the index. Structure the pipeline so different principals perform source onboarding, content normalization, embedding, and promotion to production. Require code review and dual approval for parser and chunker changes, and sign artifacts at each stage so tampering is detectable. Grant the embedder service only read access to staging content and write access to a temporary vector store. A separate, narrowly scoped promoter moves signed batches into production. Human editors can propose corpus changes but cannot run indexers. Operators can execute index jobs but cannot alter source lists. Break glass procedures exist but are logged, time-boxed, and post-reviewed. This choreography may feel slower than a single super-user script, yet it pays back by turning silent, hard-to-spot errors into events that leave evidence, and by making deliberate poisoning attempts collide with multiple, independent gates. Clear escalation paths transform anomalies into managed incidents rather than lingering suspicions. Define severity levels for retrieval oddities, sudden spikes in rare document hits, appearance of disallowed markers, answer drift on regulated topics, and map each level to actions and time targets. Low severity events trigger downranking and sampling. Medium severity adds source quarantine, index snapshotting, and targeted replay. High severity invokes cross-functional triage with security, legal, and communications. Publish who owns the pager, who can block ingestion, who can revoke retriever tokens, and who must be notified for customer-visible impact. Automate the first steps. When detectors fire, open a ticket with logs, retrieved identifiers, and relevant manifests attached, and pre-stage rollback commands. Tie escalation to business calendars, tax season, product launches, so thresholds tighten when the blast radius is larger. The objective is speed with discipline, fast enough to limit harm, structured enough to learn and improve afterward. Continuous auditing closes the loop by checking whether controls remain effective over time. Run scheduled reconciliations that compare manifests, checksums, and index counts. Any drift without signed updates is a defect to investigate. Sample retrieval logs to verify access scopes, ensuring private shards never appear in public flows, and cross-tenant queries stay isolated. Recompute embeddings for a random slice monthly to detect tokenizer misalignment or silent model upgrades that skew neighborhoods. Review privilege assignments quarterly and expire unused service accounts. Attest that least privilege policies match reality, not just intentions. Produce audit packets, provenance records, signed batches, detector metrics that external assessors can verify without privileged shell access. Crucially, audit your audits, track how many issues surface through auditing versus incidents, and adjust scope accordingly. An audited system invites fewer surprises because the routines that would reveal them are part of normal operations, not emergency archaeology. Operational governance works when it is measured. Establish key risk indicators for the retrieval layer: percentage of answers citing vetted sources, rate of quarantine shards, proportion of retrievals from high-trust collections, and review them alongside latency and accuracy in operating reviews. Train engineers and analysts on playbooks so role changes do not erase institutional memory. Conduct game days that simulate poisoned ingestions, ranking manipulation, and prompt injection payloads, then score detection time, rollback duration, and communication clarity. Budget explicitly for security overhead, context filters, grounding checks, re-ranking, so they are not toggled off during peak load. Align incentives by making safe defaults the easy path. Templates that pre-wire validators, pipelines that refuse unsigned inputs, dashboards that highlight unsupported claims. Governance is not a barrier. It is the paved road that gets you to reliable, auditable answers at scale, week after week, release after release. This episode outlined how retrieval-augmented generation expands capability by grounding answers in external indexes, and how that expansion introduces new risks across ingestion, embedding, indexing, and runtime. We examined poisoned documents, hostile vectors, ranking manipulation, leakage through embeddings, and prompt injection via retrieved text. We then highlighted mitigations, access control and tenant separation, confidentiality and integrity controls, testing and monitoring, context filtering, grounding checks, output validation, disciplined updates, supply chain hygiene, and encrypted traffic. The through line is vigilance and instrumentation. If retrieval is a door into your model, you must decide who holds the keys, what is allowed through, and how you notice when someone is picking the lock. In the next installment, we deepen the focus on context filtering, how to score, trim, and structure evidence so the generator reads only what is useful and safe, even when adversarial content tries to slip into the window. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.